On April 28, 1988, a Boeing 737-200 climbing through 24,000 feet over the Pacific suddenly lost an 18-foot section of its fuselage. The cabin floor vanished beneath the feet of passengers. This was not a rare, dramatic failure. It was the quiet endgame of a process that had been building for years: metal fatigue. The NTSB would later determine that the aircraft had accumulated 89,680 flight cycles, far exceeding the design goal of 75,000 cycles for its fuselage lap joints. Each pressurization cycle had inflicted microscopic damage, invisible to the naked eye, until the cracks linked up and tore through the skin. Metal fatigue begins with repeated loading below the material's yield strength, pressurization cycles that make the fuselage expand and contract like a balloon. Over thousands of flights, microscopic cracks form at rivet holes and lap joints, growing unseen until they reach a critical size. Then, without warning, the structure fails. Each pressurization cycle expands the fuselage like a balloon, then contracts it on landing. Over thousands of cycles, this repeated strain causes microscopic damage at the grain level of the aluminum. The metal never yields. It just accumulates tiny, permanent changes. That microscopic damage is the beginning of a crack. At first, it's invisible. A few grains of aluminum that have slipped past each other, but each cycle adds a tiny increment of growth. The crack propagates grain by grain until it reaches a critical size. And here's the catch: the material never yields, it just breaks. The ASTM defines it precisely. Fatigue is the progressive, localized permanent structural change that occurs in a material subjected to repeated or fluctuating strains, at stresses having a maximum value less than the tensile strength of the material. In plain terms, the metal doesn't bend, it just breaks one cycle at a time. So why did nobody stop it? On that April day in 1988, Aloha Airlines Flight 243, a Boeing 737-200 climbed through 24,000 feet over the Pacific. It had completed 89,880 pressurization cycles, far beyond the 75,000 cycle design goal for its fuselage lap joints. The cabin was full. Then, with a sound like thunder, an 18-foot section of the fuselage peeled away. A flight attendant was swept out into the void. The cockpit door flew off. The pilots fought to control the aircraft as wind screamed through the gaping hole. Miraculously, the pilots landed safely. But the question burned: how had cracks grown unseen for years? The answer lay in the lap joints, where sheets of aluminum overlap, riveted together, perfect stress concentrators. Each pressurization cycle flexed them, millimetre by millimetre. The NTSB found that corrosion had accelerated the cracking, and inspections had missed the signs. The accident became a wake-up call. It forced the FAA to create the Aging Aircraft Program, mandating supplemental structural inspection programs for planes over 20 years old. But why did inspections miss it? The answer lies in how fatigue cracks grow. Invisible, silent until the final moment. At a rivet hole on a lap joint, stress concentrates like a knot in a rope. Every flight flexes that tiny area, and a crack begins. A few grains of aluminum, no wider than a hair. And here's the twist: the crack can grow to critical length, inches long, while the outer surface remains perfectly smooth. The metal fails from the inside out. On Aloha 243, the crack had propagated through multiple rivet rows, hidden beneath the overlapping skin, invisible to the naked eye. The NTSB report stated it plainly. The fuselage failure was the result of fatigue cracking that had been present for many flight cycles, but was not detected during inspections. Not detected because the crack was hidden, growing unseen in the shadow of the lap joint, cycle after cycle. So how does a crack stay hidden? The lap joint is two layers of aluminum bonded and riveted together. The crack starts on the inner layer, shielded by the outer skin. Even when it breaks through, the gap may be so fine that paint and dirt fill it, masking the fracture. By the time it's visible, it's too late. So how do you catch a crack that's invisible to the naked eye? The answer came in the wake of Aloha 243, a new regime of inspections designed specifically for aging aircraft. The FAA's Supplemental Structural Inspection Program, or SSIP, mandated that planes over 20 years old undergo detailed teardown inspections of their most fatigue-prone areas. But these inspections rely on techniques that can detect cracks far smaller than the human eye can see. Eddy current testing sends a magnetic field through the metal, measuring changes in conductivity at rivet holes. Ultrasonic testing bounces sound waves off hidden flaws. Dye penetrant seeps into surface cracks, staining them bright red. Yet even with these tools, cracks can be missed. In 2011, Southwest Airlines Flight 812 suffered a 5-foot fuselage tear at 34,000 feet. The aircraft had undergone inspections, but fatigue cracking in a lap joint had gone undetected. The NTSB found that the inspection procedures at the time were inadequate for the specific crack geometry. The lesson was clear. Inspection alone is not enough. Modern aircraft are now designed with damage-tolerance principles, meaning the structure is built to survive with cracks for a limited number of cycles. The airworthiness limitations. Section of the maintenance manual specifies mandatory inspection intervals for every fatigue-prone area. So the question becomes, how many cycles are too many? For a 30-year-old airliner, the answer depends on rigorous tracking of every pressurization cycle. Each flight is logged, and when the aircraft reaches its design life, it must be retired or undergo extensive life extension modifications. Fatigue is quiet, but it is not invincible. Yet the Aloha accident forced a reckoning. The FAA launched the Aging Aircraft Program, mandating supplemental structural inspection programs for planes over 20 years old. But here's the uncomfortable truth. The average commercial jet today is 12 years old, and thousands are far older. To understand the scale, consider this. A 30-year-old 737 may have endured over 50,000 pressurization cycles. Each cycle stresses the fuselage, and fatigue cracks can grow undetected. The 2011 Southwest Airlines Flight 812 incident proved the lesson hadn't fully sunk in. Which brings us to the Boeing 787 Dreamliner. Its fuselage is made of composite materials, carbon fiber reinforced plastic, that are far less susceptible to fatigue than aluminum. Composites don't crack from repeated pressurization the way metal does. But composites bring their own challenges: impact damage, delamination, and moisture ingress that are hard to detect. So the mantra remains the same: inspect, inspect, inspect. The FAA's airworthiness limitations section lists mandatory checks for every fatigue-prone area. But how do engineers predict when a crack will become dangerous? They use the SN curve, which plots stress against the number of cycles to failure. Each material has its own curve, and designers ensure that operating stresses stay well below the endurance limit, the stress level below which fatigue never occurs. So the danger zone is often around rivet holes. When a rivet is installed, it deforms the surrounding metal, creating residual stresses. But over time, as the fuselage flexes, those stresses can reverse, and tiny cracks initiate at the hole edges. This is why lap joints are inspected so meticulously. Once a crack initiates, its growth follows a predictable pattern. The crack growth rate increases with crack length, so the final failure can happen very quickly. This is why regular inspections are critical. They aim to find cracks before they reach the critical size where rapid growth begins. Which means the inspection interval must be shorter than the time it takes for a crack to grow from detectable size to critical size. For the Boeing 737, the airworthiness limitations section mandates inspections every 5,000 to 10,000 cycles for certain lap joints. This is the safety margin. But fatigue is not the only enemy. Corrosion can accelerate crack growth dramatically. In the Aloha accident, the NTSB found that corrosion had weakened the lap joint, making it more susceptible to fatigue. Moisture trapped between the layers of metal created a corrosive environment that ate away at the aluminum. And inspections depend on human vigilance. In 2011, the Southwest Airlines incident showed that even with proper procedures, cracks can be missed if inspectors are not trained to look for specific patterns. That incident led to revised inspection techniques and more frequent checks for certain aircraft models. So metal fatigue is quiet, but it's manageable. Through rigorous inspection and modern materials, we keep the sky safe. The lesson from Aloha is not to fear the aging airframe, but to respect the cycles that quietly wear it down.